Good morning. Happy New Year. I hope you all are doing well. I'm sorry that I'm not there with you. I rather would be with you than here, but we're going to make do with what we can, and I look forward to actually seeing you all in person next week. Like I said in my email, I am available. If you have questions, if anything that we do over the next week or while I'm not there is confusing to you, reach out to me, email me, send me a message on Remind, whatever it may be, a message in Canvas, and I'll respond as quick as I can to help you out. I know this is going to be a little weird for a bit. We are starting Unit 5 today. We are going to dive right in. New year, new unit with talking about stars, the life cycle of stars, how we measure stars, how we can know all sorts of different things about stars. And we're going to start by how do we understand how far away they are. So here is kind of the stuff around us, the neighbors closest to the sun. And let me move me so that you can see the words a little bit better. As we move away from the sun, we need to figure out a different method for measuring things, right? We can measure the distance to the sun in 8 light minutes. Most of the time, we say that the sun is 1 AU or astronomical unit away from the Earth. And that is the definition of an AU, like we've talked about, is how far is the sun away from Earth. So for things in the solar system, we typically measure in AUs. We'll say that the outer planets are 20 to 30 AU away from the sun, and so on. When we move farther out away from the sun, an AU doesn't cut it anymore. Things are really far away in space. It's called space because there's a lot of nothing. So we need a different unit. So we use light years. Probably, hopefully, we've said it before. A light year is how long it takes light to go that, or how far light can go in 1 year. So with here in this picture, it shows the Oort cloud is a little less than 2 light years away from the sun. So it takes a little bit less than 2 years for light from the sun to reach the Oort cloud. Here, Proxima Centauri and Alpha Centauri are the closest stars to us, besides the sun, the closest other stars, and they're each about 4 light years away. So if you look up at Alpha Centauri, you are seeing what it looked like 4 years ago, because it took 4 years for the light to reach us. But that's a kind of nebulous, weird term, so we need to figure out or need to think about how many kilometers is 1 light year. So the speed of light is about 300,000 kilometers per second. We are in a science class, so we're going to use kilometers. If you prefer miles, then go ahead and pull up on your phone a kilometers to miles converter. I'm going to be talking in kilometers. And to go from speed to distance, we multiply speed times time. We said this is a light year, but our speed was measured in seconds. So I need to figure out how many seconds are in a year. I'm going to round a little bit, 365 days approximately, times 24 hours in a day, times 3,600 seconds in an hour. All of that to get me to about 31 million seconds in a year. This 3.1 blah, blah, blah times 10 to the 7 seconds, the number of seconds in a year. So now distance equals speed times time, multiply my speed times my time, and I get this 9.46 times 10 to the 12th kilometers. That is 9 with 12 other things after it, or 9.46 trillion with a T, trillion kilometers. That is an absurd number, and humans as a species are really, really, really bad at wrapping our heads around big numbers like that. It's just like a flaw in our psychology. Humans are bad at understanding big numbers. So let's try and take this and see if we can figure out what it is. What is 9.6 trillion kilometers, or what does a trillion even really mean? So, if you had to guess, and I'm going to pause, how long do you think 1 million seconds is? It's about 11 and a half days, closer to 12 days maybe. So you've lived a million seconds. You've lived a million seconds a dozen times over, more than a dozen. You've lived a million seconds a bunch. About 11 and a half, 12 days is a million seconds. What about a billion seconds? If a million is 11 and a half days, how long is a billion seconds? I have not lived a billion seconds. You have not lived a billion seconds. None of us in this room have lived a billion seconds. A billion seconds is 31.7 years or 32 ish years. So that's a big jump, right? We went from 11 and a half days at a million to 32 years at a billion. So it's not like a small step up to go from a million to a billion. It's a massive jump. We're multiplying what we had before by 1,000. So if I'm going for a trillion seconds, same idea. Any guesses? A trillion seconds is going to be 1,000 times bigger than a billion seconds. So a trillion seconds is 31,000 years. So a trillion is a big number, and we're talking about 9 trillion miles or kilometers away. And so 31,900 years for a trillion seconds, and we were looking at trillions of miles away. So things are really far. I do have here 41 trillion miles, the closest star to us, 41 trillion miles, or 25 trillion miles. Massive distances. And so when we're talking in astronomy with these massive distances all the time, it's exhausting. I don't want to say 41 trillion kilometers all the time. So instead, we use light years, just a different scale to measure the same thing. But how can we actually figure out those distances? We can't go 41 trillion miles away. We don't have spaceships that could go there. Again, if you think about the idea we maybe have talked about before of like a generation ship, our fastest rocket ship ever would still take thousands of years to reach the closest star to us, Alpha Centauri or Proxima Centauri. Proxima Centauri does have an Earth like planet around it, but it's a little bit too close to the star. It's probably too hot for there to be any life there. But, maybe we could do some terraforming. But still, even our fastest ship having to go 41 trillion miles or 4 light years would take thousands of years. So in sci-fi and maybe in reality, I don't know if people in space industries actually talk about the idea of a generation ship, is having a ship that could entirely sustain life loaded up, knowing that the first people to get on the ship aren't going to be the ones who land on the new planet. Multiple generations are going to live their entire lives on this ship in order to reach a new planet. But right now we're not there. We can't even get to any of these stars. So how do we actually know that this is how far away these stars are? And before we get into it, I'm going to give you an example. We are going to look at a star called Barnard star. That's not a typo. I'm not mispronouncing it. It is named for a guy, Barnard. And this is one of the closest stars to the sun. It is in the constellation Ophiuchus. So here is one image of Barnard star. It's the bright one in the middle. And here is another. I want you to take a second and look at these two pictures and see what it is that you notice. Pay close attention to the dates at the top. If you haven't noticed or don't see it, here is Barnard star that we're looking at. So take a second. What's just something you notice about this star? Hopefully, probably, you notice that that big bright star has moved. Its relative position has changed. Why do you think that is? Why do you think Barnard's star has moved? So the stars are moving in the sky. We've talked before about how they twinkle because of atmospheric distortion, but that's a lot more than just a twinkle, right? That star has moved a lot. Hopefully, you noticed on the dates that these were about 6 months apart. We have from the two kind of opposite ends of the year pictures of this Barnard star, and it's appeared to move. It's not that Barnard star is orbiting anything, but it has to do with the fact that Earth is orbiting the sun. And when we look at Barnard star from slightly different positions, it looks like it's moved against its background. This is an effect called parallax. Things that are close to us appear to move relative to their backgrounds when we move. Earth is going around the sun, and so when we're on one side in January, we see the stars that are closer to us against a certain set of background stars. But 6 months later, in June or July, when we're on the other side of the sun, the background stars appear to have changed. This is called parallax. The stars aren't actually moving. It's that we are seeing from kind of different angles what or how those stars have changed against the background. This really only works for up to about 1600 light years away for stars. And this is something that you have seen before. This is something that you can look at besides stars. One way you can do this is if you cover one eye and hold your finger out in front of you, pay attention to kind of what your finger is in front of. So for me right now, my finger is blocking the corner of my computer screen. But when I switch and block the other eye, it looks like my finger has jumped. I can see that the background has shifted, or where my finger is in relationship to the background has shifted. This is also if you've ever been like riding in the back seat of a car and pretending you're in some emotional scene in a movie or whatever, and you notice that the trees and bushes closer to the road look like they're moving a lot faster than the trees and bushes and billboards or houses that are further away. That's parallax. That's that some things are kind of moving at a different speed relative to their background objects. And it has to do with the fact that you are moving. Those two trees are staying the same distance away from each other, but as you move by, you see them kind of in a different relative position. Going back to kind of experimenting with parallax and your finger, I want you to try it again, but hold your finger really close to your face and compare how much your finger jumps when you hold it really close to your face versus when you hold it really far away from your face. What do you notice when you try that? Hopefully, you noticed that when something was closer, you can see a bigger jump. In general, parallax sizes are going to be really, really small, a fraction of an arc second. Let me back up because we haven't really talked a whole lot about arc seconds. Remember, towards the beginning of the year, we talked about degrees, and we said you can kind of measure how high up something is in the sky using your hand is like 10 degrees. So I can see, oh, a star is 40 degrees up by measuring the size that way. Sometimes we need to be more precise than we can be with degrees. So we break degrees down into arc minutes. There are 60 arc minutes in 1 degree. Again, sometimes we want more precise than that, so we break it down even further into arc seconds. So there are 60 arc seconds in each arc minute, and there are 60 arc minutes in each degree. The moon takes up about 31 arc minutes. The full moon is about half a degree. And for reference, if you hold your pinky out at arm's length, your pinky is about 1 degree. So you should be able to block the full moon with your pinky. If you look at this table that I've got, though, you might notice that there are some really, really, really tiny parallax angles, really small numbers. All of these are a fraction of an arc second. So remember, 1 degree gets broken up into 60 arc minutes. 1 arc minute gets broken up into 60 arc seconds. 3,600 arc seconds in 1 degree, the size of your pinky. Break your pinky up into 3,600 little sections. Those are each 1 arc second. And here, this star that is only 4 light years away from us has a parallax angle of less than 1 arc second. So these are tiny, tiny numbers. I'm going to throw you for a loop here for a second. Do you remember Aristarchus? He was one of the astronomers that was in our scavenger hunt in the very beginning of the year. And you might remember that he was the first person, actually, before Copernicus, to suggest that the sun is at the center of the solar system. Years and years and years before anybody else was saying it, Aristarchus in ancient Greece in the year 300 BC suggested that the sun was at the center of the solar system. He also said that the stars, those bright lights in the sky that the Greeks were connecting the dots with, were other suns. He thought that the sun and the stars were the same thing, which turns out he was right, and that they were all really, really far away. Everyone else was like, no. If those were other things that were different distances away, if there were some stars that were closer to us and some that were farther away, then we would be able to detect parallax, which is true. If there are things that are two different distances away, we should be able to see parallax. And we can, but Aristarchus couldn't. Those were tiny, tiny numbers. I mean, look at Rigel, which is a huge bright star that we now know is about 800 light years away. That's 0.0037 arc seconds. And one arc second is 1/36,000th of your pinky. These are tiny angles. So Aristarchus was right. The stars are different distances. And so there should be parallax. But, we can't really be upset with the other ancient Greeks because there is no way that that is something that you could detect with the human eye. Even the largest one we have here, Rigel Kent, you cannot detect that much of a change with the naked eye. You need a telescope. And the ancient Greeks didn't have telescopes. So these are teeny, teeny, tiny little angles we're working with here. And here is kind of what we see when we graph it, when we put distance versus those parallax angles. And so take a second, and what is something that you notice about this graph? Yeah, the farther away things are, the smaller the angle. We even had to cut this graph off. I took all of the stars from this table, and you'll see that Rigel, Antares, Deneb are all too far away. They didn't make it onto my graph because if I had graphed them, you would have been able to see basically nothing. It would have been almost impossible to even see the curve, which is an inverse curve. So the farther away that stars are, the smaller the angle. And so that is a way to measure distance. But from this, we also get a different unit of distance. We've been measuring distance in light years, but from parallax, we can get a different unit to measure distance. That distance is a parsec.
Han Solo. I'm captain of the Millennium Falcon. Chewie here tells me you're looking for passage to the Alderaan system. Yes, indeed. If it's a fast ship. Fast ship. You've never heard of the Millennium Falcon? Should I have? It's a ship that made the Kessel run in less than 12 parsecs.
Han Solo lied to you. I know that in later things in graphic novels or whatever, they tried to come up with an explanation for this. That makes it sound like parsec is a unit of time, and that is a super, super common misconception. I mean, it has SEC, it's got sec right there in it, which makes you think second. Parsec is a unit of distance, not a unit of time. A parsec is the distance to a star that would create a parallax angle of 1 arc second. It is a parsec because it is a parallax second. If I had a parallax angle of 1 arc second, then I would have a star that was 1 parsec away. 1 parsec is about 3.26 light years, so they're pretty similar scale, and astronomers will use those interchangeably. Maybe more often parsec for things that are farther away because it's a slightly larger scale. But you can see this kind of triangle graph here where the Earth is 1 AU away from the sun, 1 astronomical unit. And if I have that parallax angle of 1 arc second, then that star is 1 parsec away. We don't have that. There are no stars that are 1 parsec away. All of the closest stars are a little bit farther than that. All of our stars are just really spread out in space. So, measuring parallax is one way to measure stars. But like we saw, there's kind of a limit with that. The angles get really, really, really small, really, really, really fast. And so, stars that are too far away, even with our best telescopes, we cannot detect parallax because the angle is so insignificantly small. So, we can really only use parallax and parsecs to measure distance that are fairly close to us. But the universe is really big. There are a lot of stars that are a lot farther away than that. So we are going to, throughout this unit and throughout the rest of the year, look at what we call the distance ladder. How can we find stars farther away, kind of step by step? So the first step is parsecs and parallax. What are the things that are kind of close to us where we can actually see the stars moving relative to their backgrounds? We're going to get into throughout the rest of this unit a couple of different methods. And one thing that's going to kind of remain throughout the whole unit is this idea of what's called a standard candle and how a standard candle relates to the distance ladder. You've probably realized this. The farther away you are from a light source, the less bright it is, right? If I shine a flashlight at your face, if you step farther and farther away from it, it looks less bright. That's because the light has to go out in every direction and it gets spread out evenly in every direction. So if something's really close to you, a lot of the light is going to be hitting you directly and it will look really bright. If something is much farther away from you, the light has had more time to spread out and not as much of the light is going to be hitting you. Like with this candle here, when I'm really close to the candle, most of the light is hitting this one tiny spot. But the farther away I go, the more time the candle has had to spread that light out and the less bright it seems. This is going to be a really recurring thing that we have in this unit and throughout the rest of the year. This idea of the inverse square law, that as things move away, the brightness decreases with the inverse square, or the is related proportionally to the inverse square. That is what you're going to be looking at with for the rest of class today. Is an assignment shared with me by Mr. Davies at Liberty about how can I measure how bright something is based off this distance.